Hello, everyone, and thanks for joining us for the Advances in Battery Research 2025 online symposium. I'm George Hammond, and I'm here to moderate today's event alongside my colleagues Princess Sennett and Heather James. Before we start the talks today, I just have some general information and a few tips for getting the most out of the event. We would like to ask if you could please refrain from video, audio, or photo recording of all talks. Many of our speakers have kindly agreed to share their slides with you, and these are available within the literature section on the platform. Please remember that we encourage debate and discussion and welcome all of you to use our networking services to introduce yourselves to other attendees, but we do not permit the overt solicitation of products or services and reserve the right to block any user who infringes on this rule. It's also incredibly important to say that this event was only made possible thanks to the generosity of our sponsors and partners, particularly our platinum sponsor, PerkinElmer. For more detailed instructions on how to make the most out of the features available to you at this event, please navigate to the event home and watch the overview video at the top of this page, or visit the FAQ section in the left-hand menu. And with that out of the way, I will now move on to introduce our opening and keynote session for the event, for which I'm pleased to welcome Professor Weihan Li presenting his talk, Digitalization and Acceleration in Battery Testing with Machine Learning. Professor Li is a junior professor in artificial intelligence and digitalization for batteries at RWTH Aachen University, where he leads a research group within the Center for Aging, Reliability and Lifetime Prediction of Electrochemical and Power Electronic Systems. Professor Li's research focuses on leveraging artificial intelligence and physics to drive digitalization in battery technology. A very warm welcome to you, Professor Li. And following the presentation, we will also have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. And without further ado, I will now hand over to Professor Li to begin his presentation.
Yeah, thanks a lot for the introduction, and thanks again for the invitation for this talk. So today I would like to discuss our recent research in digitalization and acceleration of battery testing with applications of AI and the physical models. So I would like to start with a short introduction about our research center and my group. So I'm from Aachen University, where we are located in the Center for Aging, Reliability, and Lifetime Prediction for Electrochemical and Power Electronic Systems, where we are working on supporting battery applications, production, and material design. And this is the very challenging part for Europe right now because we would like to develop our own battery technology here in Europe. And to achieve that, we need to have a very special facility to understand battery aging and reliability from the particle level to material level and further on cell level and system level. And how to connect everything together. That is the mission of our center here in Aachen. As you can see here from this circle of innovation from our research center, so we would like to provide the platform for research from ions and crystals to battery packs and systems. And a lot of data will be generated, right? So not only within this center, but also from our industry partners, because we are also working widely with German and European industry partners from production to application in the cars and also in other application fields like stationary energy storage system, further to second life and the recycling. And there will be different kinds of data be generated, right? Time series and images. And with all of this, we would like to develop digital tools to extract information from all of this data. So we have a quite a strong post-motive laboratory, which is very helpful for us to open the battery cells to carry out post-motive analysis, not only for fresh cells, but also for aged battery cells, different technology, not only lithium-ion battery, but also sodium-ion battery and solid-state batteries. And here we use different devices to understand the aging on the material level, right? So on the mechanism level, and further, transfer this information and data to battery modeling. So we are also doing a lot of battery testing and the performance evaluation aging test. And for that, we have more than 5,000 battery testing channels covering all the current ranges, and for small commercial cells, cylindrical cells, to pouch cells and prismatic cells, and further to battery modules and battery systems. And we also design the power electronics because, as I mentioned before, we are the group also very active in power electronics and reliability of it to further support the battery testing with new sensors and measurement technology. So if we further look at battery sensor technology, we are mainly working on new sensor technology to extract more information related to the electrical, thermal, and aging behavior of batteries. For example, pressure measurement, for example, using fibers to measure the temperature of the batteries and use ultrasound to do battery diagnosis, right, to understand the mechanical changes within the battery without opening the battery cells. And on the system level, we also need to understand what are the influences of different environmental loads on battery cells and battery systems. For example, the influence of vibration. For that, we have different shakers to um, um, investigate the influence of different vibrations on cells and systems to further optimize the system design. And pressure is a very important topic, and also similarly, the mechanical deformation of battery cells, especially for pouch cells. We need to understand it with optical measurement. And other effects from the environmental loads is, for example, the temperature influence, right? So for that, we have the testing environment here to change the temperature very fast, right? So to understand the thermal stability of the batteries. So the last topic will be the pressure, right? So as I mentioned, so pressure, really high pressure and low pressure for some specific application, for example, in space, we need to understand whether the current cell and the system design is reliable enough for such application. And with all of these facilities, we are able to generate data, and we further develop models, tools, and methods to analyze such data, right? So to further digitalize the way we model the batteries, we use the batteries, and the way we optimize the batteries. And that's the focus of my group. So we are uh, on the viewpoint of data scientists, AI specialists to help the experimentalists to develop digital models, to integrate them in production, in battery testing, application, and second life, to enhance our understanding and further improve the performance of the models for prediction, optimization of battery management, and even the strategy of use of batteries. And today, I would like to give you some very concrete examples how we are doing that with the focus of testing. Yeah, I will not touch other topics. You can, follow our recent publications for other areas. Um, why the digitalization of battery testing is important? So, as I mentioned before, production of batteries in Europe and for Europe is very important. And that's also a lot of players who are working on this direction right now in Germany and also in Europe. But batteries need to be designed and produced to meet specific requirements for different applications. We know that the requirements for high performance cars and the stationary energy storage will be different. And basically speaking, we need to have a look what are the requirements on energy density, power density, cell to cell variances, and battery aging and safety. And this is really tricky because the evaluation of such performance or indicators need to be done very fast during this, optimization phase for the production, right? So the production needs very quick feedback from us, right? From end of line tests or from further evaluation processes, so that we can give them very quick feedback to help them to understand, okay, what is the problem right now and how can they further optimize the production line. On the other side, when the battery cells are produced and they are delivered to OEMs, right, for all the possible applications, the OEMs also need to do quick battery tests or even accelerated aging tests, right? So to understand whether the battery cells meet the requirement and how can they develop aging models, safety models to guarantee the warranty, right? So for the users, for their clients. And to do this, right, so they need to also accelerate the whole process, right, and then further to meet the customer confidence and further reduce the cost of the whole developed cost of the battery and battery systems. So what is the state of the art? State of the art tests for end of line tests is usually done by charge and discharge processes to measure the capacity of the batteries, and we can do like post test to measure the resistance in quite an easy way. So this kind of tests usually takes hours or days, right? But the difficulty here is that we can extract electrical parameters like capacity and resistance from this kind of tests, which is quite difficult to be correlated with battery aging. To achieve a better understanding of aging, so the standard way we do is the so-called accelerated aging test, right? So there are a lot of stress factors that will have influence on battery aging. For example, time, right? For example, the charging, discharging current rates, right? This depth of discharge, right? So C, temperature, and if we further think about the reality, right? So the battery will be there, not used, especially for like private cars, right? For almost 90% of the time. So the rest time will be important because calendric aging will happen. And the battery cells are also not being used like with constant current and charge and discharging. They will be, charge and discharge with dynamic profiles, right? So what is the influence of that? With all of these complex stress factors, right? So we have a very long testing duration to understand the correlation, the influences of everything. And usually it takes us months, even years, to achieve a better understanding of battery aging. So the solution we are providing, or we would like to provide here in CAL, is to automate the characterization of battery performance and aging at physical parameter level within several weeks. How can we achieve that? The key tool that we are using is, first of all, automation. We are automating the testing process with robotics. Second thing is digitalization. We are analyzing the data with AI and develop digital models to integrate them further into characterization tests and aging tests, and further use AI to help us extract information about the physical parameters from the data and build up aging models which will further help to reduce the number of physical tests by replacing them with digital tests. And with all of this, I would like to give you several examples on these different kinds of topics so that you can have the basic understanding what is the future direction in this. So I will start with automated characterization tests. So what is the standard optimization we can do, right? So for characterization. Characterization is very important, but it's very challenging. We are not talking about characterization to get only resistance and capacity. We are talking about how can we get more information on the physical parameter level. On this page, I'm trying to summarizing the standard way or state of the art for us to parameterize a P2D model or physical model, right? So we need to open the battery cells, right? So we need to then prepare the materials and then use different testing devices and the methodology to measure each of these parameters, right? Some of them are geometrical parameters like particles, like the thickness of the layers and electrodes, and then furthermore like porosity and so on. They can be then further measured by other approaches. And the whole process is very time consuming, right? So according to our experience, the state of the art where we do it in currently in our laboratory, we need several weeks to finish a parameterization of physical models for a fresh cell that we do not know. Can we accelerate it? Can we do it with less effort in the chemistry? That will be the question. What we are working on is to further develop the automated characterization test with design of experiment to enable the characterization of the batteries on multi-scale. So as you can see, we are not only using the standard cell tester, we are also using or integrate other sensors or testing methodology like EIS measurement and, for example, micro CT and infrared camera system into the characterization so that we can extract more information from this short-term characterization test to understand the performance of the battery cells related to electrical, thermal, and mechanical information. So this is some ongoing work that we are doing now. As you can see, we are building up these robotic systems to further automate the way we do cell testing, ES measurement, and CT measurement. So at the end of the day, we will have this automated system where when the cell delivered, we can use this system to accelerate this whole characterization process and generate multi-dimensional data, not only electrical test data, but also CT and thermal images. And this will be the foundation for further identification of all the physical information from this data set. And this further allowed us to understand the effects of material and process changes in cell production, right? So, and then give this feedback to the production line. And but how can we do that, right? When we get this data, our idea is to use AI as a tool to parameterize the physical model. We know physics is quite complex, right? So we are not using any black box model here. We still keep the physical model as it is, right? So what we try to do is to avoid open the battery cells, but use other sensor technology to do non destructive measurement like electrical tests, like CT, like thermal images, to give us a lot of information which help us to use AI as optimization tool to identify the values of the physical parameters, which will further save us a lot of time, cost, and further increase the accuracy. I will show you step by step how can we do that. The first step, before we start this identification, we need to understand whether all the parameters can be identified, right? This is exactly the sensitivity analysis. So what we do here in this step is to understand in this value range of the battery parameters, what are the identification ability of the parameters if we change this parameter within this range for different input profiles, right? So like constant or high dynamic profiles. And with this, right, so we have different methodology, like one at a time method, which is local method. We also have like global sensitivity analysis method. We will not touch the details here, but I would like to show you some results here. You can see on the right hand side. Yeah, so this is some results of sensitivity analysis for two different chemistries. One is NCA as cathode and blended graphite and silicon as anode material, and the other on the bottom is FP and graphite. And you can see the chemistry change has a strong influence on the sensitivity of the parameters. This is, for this case, especially because of the plateau of the FP cells in the OCV curve, which decreases the sensitivity of a lot of the capacity related parameters, which usually they have quite a high sensitivity in the MC and NCA cells, which can be quite easily be identified. So these results show us, so for different cell design, for different cell chemistry, we need to always start with understanding the sensitivity of them, because this will be very helpful for us to further optimize the way we identify them further. How can we identify them? Yeah, so this is one example how we can do that. There are a lot of algorithms that can be helpful, right? Like global optimization algorithms, like other algorithms, like even machine learning algorithms, like bias optimization algorithms. But the basic idea here is to use the information from sensitivity analysis. And here, as you can see, we have grouped the parameters into two groups, and the first group are quite high sensitivity parameters, and we try to identify them with machine learning and AI algorithm in the first step, and then we fix them. We do not change them anymore, because if we keep changing them, right, so they are very sensitive, right? So a small change during this optimization process will give a very strong influence on the changes of the voltage, right? So which is the output of the model. This will make the identification of the low sensitivity parameters very difficult. And by doing this, we are able to have this pipeline to identify the physical parameters in multiple stages. And the other interesting thing here is what we have learned from machine learning is the way we do this identification is also very similar to if we think about machine learning models like neural networks. We are parameterizing the model, right? The difference is the model structure. Here we have the physical model, we have the physical model structure, and the neural network you have like neurons, right? So, but the way you optimize it, you learn from the data by comparing your simulation and the experiments, the measurement, and then calculate the errors and then feed it back to the optimization is very similar. But both of them are facing with a difficulty, which is the limitation of the data set. uh, very significant for parameterization for battery cells, because we would like to reduce the number of battery tests that we would like to do. The data set is quite limited, right? So we usually have several data sets compared to machine learning models is quite limited. That's why how to avoid overfitting is very important. So what we would like to provide here is we can learn from machine learning, the way we train machine learning models, the way we train neural networks, right? We can use similar strategy, right? To divide the batteries into different groups. We can do cross validation and so on and so on. And that is correct. We must do that to avoid the overfitting of this, optimization process, because it could happen because of the low sensitivity of several of the parameters. Some results as examples. This is for COCAM cell, MC as cathode, and graphite as anode. And the experimental data set, what I'm showing on the left, is the state-of-the-art method we use in the chemistry lab by opening the battery cells, by measuring every parameter step by step with different devices. And the data-driven, what I'm showing in the middle, is the method that we are developing and we are providing here. As you can see, by comparing them, we see that the data-driven approach we are working on is very good compared to experimental method where no optimization is happening, and we are able to reduce the error in both like low dynamic profile and high dynamic profile, like driving cycles, significantly. And this also helps us, right? So to further prepare a model that is ready to be used for simulation and BMS. Yeah, and I don't want to say that we need to replace like, our work in chemistry lab, because the chemistry lab work is very important, especially for new chemistry, like the chemistry where we do not know a lot, where we do not know what are the value boundaries for each of the parameter, right? Because we do not see a lot of parameter yet in the literature. Yeah, that's why this two methodology can sometimes also be combined together, right? We use the state-of-the-art way, right, to parameterize in chemistry lab if we are allowed to do that. And then we use this method as the second step, right, for a further optimization or a fast identification of the parameters. This can be well connected to battery production because for battery production lines, they know several parameters already, like the particle size and the others, right? So then they can use this tool at the end of the end of line test and quickly parameterize the electrochemical model and understand, okay, what is the performance of the battery cell and what is the reason for this bad performance, so they can focus on this parameter directly. The second part, after we do the characterization, we need to do aging tests, right? We need to develop aging models. But how can we accelerate that? What we are working on here in Aachen, in my research group, is to use this very special testing device. So where we have more than 2,000 battery channels, right? So with this special mass cycle test benches to create a very comprehensive data set for battery aging. What we are doing in the way of like digitalization is to integrate the battery diagnosis and prediction models in our testing system. Right? We are not using like open access data sets to just run some algorithms for fun. We are really integrating the models we have developed into the testing of the real cells that we are working on. By doing that, we can then further use machine learning to help us to make decisions during testing. Okay, what will be the next step? Where should we further test? This is all based on the aging model that we are parameterizing during testing. Yeah, and then a lot of algorithm can be helpful in this decision making. For example, reinforcement learning. For example, Bayes optimization. And this online design of experiment for aging test is the future direction that we need to work on to further digitalize the way we do battery tests to help us reduce the time, reduce the cost, and I will show you several examples what is the current progress. So first of all, how can we do this online diagnosis without opening the battery cells while we are still doing tests? Right. This is one a good example that I would like to show. We have developed very good approaches where we are able to do battery aging diagnosis not only on the capacity fade and power fade level, but also to understand what is the degradation mode and even impedance. Right. So without carrying out specific measurement like EIS measurement, we just use load profile or dynamic profiles that we can get from the characterization or the testing procedure. So the basic idea is we use the battery model, right? It could be like parameterization of equivalent circuit model or some other models. And then use the data set during aging to parameterize the models in the same time. And with the output of this approach, we can further understand what is the current aging mode, what is the current batteries, and how can we further, predict the future of the battery degradation with this specific cell. And some results. So this is based on purely field data, right? So we are not using any like very accurate QCV measurement or pulse test or other kind of characterization method. We are just using field data, right? So very dynamic profile to reconstruct the OCV of the batteries. And with these results, you can see that on the left-hand side is the measurement, and on the right-hand side is the identification results. We can build up the OCV quite accurately based on a very well observable chemistry, because this is the as I said, the NCA and graphite silicon battery cell. And we also have similar results for FP, but which is much more challenging because the plateau of the OCV really gives us much more challenge in identifying or reconstructing the OCV. And based on this reconstructed OCV, we can further identify the aging modes, right? So there are several methods that can be done, and we can further understand what is the LI, LAM for cathode and anode, and with all of this information, we can further do the prediction more accurately. So with this kind of diagnosis tools, right? So we can further integrate such tools into our database. So the PhD student is working on building up this database in our institute with the integrated data analysis tools. Here, what we would like to do is to use CADI format, which is a quite famous database from KIT and widely used here in Germany for battery research, for battery data collection. And here we build up this interface and data for this database so that we can catch all the information we need during testing and then further integrate these diagnosis tools into the testing. So to do real-time analysis of the aging results. And with that, we are able to further develop or parameterize, right? So for example, here, Elias is working on empirical model. We are parameterizing the empirical model during testing, and we will check what is the uncertainty of every parameter that we need to parameterize, which will further help us to determine what is the next point that we need to test. And we can also use machine learning to achieve that, right? This is another example where we are also working on in Digibot project and also Speed project that Renyang is working on machine learning algorithms for battery lifetime prediction based on the very early stage battery aging test data to have a much higher extrapolation ability because extrapolation is very, very challenging for both physical models and machine learning models. And here we further use design of experiment to help us understand what is the most efficient way that we can test further. We can replace the cells where we already have enough information and then further use another cell to be tested for another direction and to further at the end reduce the total time we need. Yeah, so with characterization and testing for aging, right? So we are generating a lot of data set, right? So, but how can we do with this huge data set? We need to have further tools, right, to help us analyze the data, do pre-processing, and prepare the data set for further modeling step. As you can see on this page, I'm listing several data that we will generate within this frame, right? So we will have electrical tests, we will have even EIS measurements, the spectrum of EIS, we have the thermal images, we have CT images, and they are multiple dimensions, right? So 1D, 2D, 3D, with time even 4D. And the standard way we do for lifetime prediction is we use the capacity and resistance, right? So this aging indicators where we get from the electrical test. But this is very challenging for prediction, as I'm pointing out here. This data set I'm showing on the bottom is about 50 battery cells that we have tested in car in Aachen from the same production line. You can see at the beginning, very beginning, there's no difference, right? There's no significant difference in the degradation at all. But if we test it further, we will see that for the end of life, for first life and second life, where I'm marking them as yellow and red curves here, they have as high as almost 400 to even 500 difference, right, in cycles. And how can we achieve this early prediction? The information we would like to highlight here is to increase the information from multi-dimensional data set, as what we are doing here, right? From CT, from thermal images, and so on. We can use AI and machine learning models to help us to identify the unknown data patterns and correlations, right, from very early stage data and the battery lifetime. And some examples, right? So Thorsten is working in the group in the direction to digitalize the way we do data analysis for figures. So this is an example where we try to enhance the city images with deep learning. We need to do like denoising, right? So we need to achieve high resolution city images for battery material characterization, where we try to reduce the cost in the measurement, right, with a much faster measurement, a little bit cheaper measurement, and but we can enhance it with AI, with deep learning models, so that we can have cheaper measurement plus AI with higher quality and higher scale of information from these images. We can even do like alignment, right? So between different data sources, right? So for one understanding of mechanism, we can use different measurements here. For example, use both SEM and CT. They have both advantages and limitations, but how to align them together will be the second step, right? So we can carry out the measurements first, and then use the alignment model that we are developing here with deep learning to align the information. You can see on the right-hand side, this is the aligned information from both images, which will directly give us enough information, right? So for this overlay comparison. So the red is the original and the green is the predicted, or let's say estimated, right? So for this alignment accuracy. Um, so what we are also working on is to further enhance the model that accepts the multi-modality input, right? So we can merge the information from different image types where we have aligned the images, and then we use the information from both to help us understand and to segment and to do prediction based on both information. And the very exciting part is we are, as I said before, we are working on identification of the parameters, right? So based on CT. And here you can see we are developing digital tools and AI algorithms that can help us to identify the geometrical information or geometrical parameter of the battery cells. Yeah, so that we do not need to do it manually, right? So with expert in the chemistry lab. This will bridge the gap between this imaging technology like CT and the battery characterization. With this, I would like to further talk about what we can do to accelerate the aging prediction, aging modeling, and and also in the direction of parameterizing the aging models with AI. So after we have all the data sets from characterization and also from aging test, we need to find the perfect model structure, right? So that we can model the battery aging with a very powerful model structure, which is able to catch all the information on one hand, and on the other hand, this structure should be explainable, right? So this should not be some black box model, because I mean the industry is quite afraid of black box model right now, because sometimes these models, if we do not have enough data set to train them, we will have some difficulty to guarantee the generalization ability of such models. That's why our approach is always to try to integrate physics and machine learning together, right? There will be different ways we can do that. One of the approach will be we can use machine learning to enhance the physical model, right? By modeling the unknown mechanisms which we do not have yet very good physical model. And on the other hand, we can use AI as a tool to further help us to quickly parameterize the physical model with this large data set. And the goal is very clear, that we would like to not only predict the future degradation of batteries in the sense of capacity fade and the resistance phase, we also would like to understand other indicators, like not only electrical indicator like impedance, like also mechanical and thermal indicators like expansion of the batteries, and whether we are also able to predict the aging modes, right? So to further understand how can we reduce the aging in the future? How can we optimize the operation of the batteries in the future? And all of this, the final goal will be on the physical parameter level, right? If we are able to track how the physical parameter will further develop, right? So in this aging process, this will be very powerful for us to give a quite fast and accurate prediction and further feedback to the production line. Some examples, we can do physics, right? So physics-based modeling is very powerful. And in this study, we present an approach to implement an elastoplasticity model for powder materials into the porous electrode theory by decomposing the overall deformation into different parts and using the powder plasticity model to describe the plastic portion. The model can capture the reversible thickness change caused by lithium-ion intercalation and deintercalation. And this is a really nice collaboration with MIT and Junior from Northeastern University. And but for some cases, right, so the data or the process, we do not understand the physics very well. This is a very good example, the formation. Formation is very important for aging, right? Because formation, a good formation process will have lead to like slow aging of batteries, and the bad formation will lead to a very fast degradation. But how to model the formation process is very, very challenging. I think there are several approaches where we are trying to use physical model to model this, but the state of the art P2P models is quite challenging in these tasks. But sometimes, if we, especially for the production lines, for production companies, they have a lot of data set, right? They have collected a lot of data, not only from the formation process, but also in the aging test, and also from other processes in production. A lot of sensors are integrated, and this is a very noisy data, but a large amount of data, right? So for such cases, we'll have a big data but small physics. For that, we can use machine learning to help us to understand what are the correlation, what are the most important features, right? So what can we do to understand and then model this and then help us to do something meaningful, right? So for example, we have showcased the two important tasks we can do with formation data. The first one is quality classification, right? So we can use formation data to help us to enhance the quality classification, right? To increase the accuracy compared only use the capacity and resistance, for example. And we can even also go a step further to predict, okay, which battery cells, which batch of the production is having a better lifetime, right? So this will be helpful to be, further feedback to the production line to help them to further optimize the production. And some example here as results, right? So we are able to achieve a very high accuracy quality classification for this data set. So the data set is from University of Michigan, from Anna's group, and this show us the potential to further digitalize the way we analyze the formation data. As I mentioned in the beginning, right, so in this part, I do think that combining physical models and machine learning is the correct direction for the future. And that's also the direction that we have worked on in the past years. And this is a really nice collaboration with UC Berkeley, Scott Morris Group, a very nice perspective paper for Nature Communication Engineering. And here we summarized the different possible methodologies, strategies that we can combine the strengths of physics and machine learning. And you are very welcome to have a read, and any question, please come to me, and I will be very happy to have discussions with you. So at the last part of our discussion today of my talk, I would like to talk about, okay, once we have the models available, how can we do further to accelerate this production, right, optimization? So the methodology is as follows. We will need to have this cell level model further to scaled up to the system level, to build up this system level model, to then do simulation to simulate the real application cases, right? So we call it as a virtual test, which will be further able to reduce the number of physical tests, right? So we can extend the testing conditions that we haven't achieved in the testing phase, which will be very helpful to understand what is the limiting parameter, right? So on the physical parameter level, that will limit the performance that we need for this application, right? So this, as I said, this finally close the loop of all the steps we have introduced before. We will then provide the constraining physical parameters to the production line to help them to like optimize the production line, the performance of the produced battery cells. And some examples, the ongoing research. This is a very nice work from Daniel in the group, and he's working on physics-based battery pack modeling, considering the influence of battery pack design. And we can, so what we are using here as a tool is Julia, so which was originally developed by different groups, and we think this is a very helpful tool in pack level simulation, because the advantage of Julia is very fast. It's much faster than a lot of other models for example, in Python, for example, in MATLAB. But we are also working closely with PyBAM team and other groups, similar direction. We try to accelerate the way we do pack level simulation with PyBAM and also our own battery simulation tools in C++. And some results are shown here for this Julia platform that we are developing. So we can see the obvious differences in current distribution among the battery cells, which reaches the maximum at the end of the discharge stage. Another work which was just accepted for publication, will be online soon in the journal, is we are working on pack level simulation platform, which will be made open access for everyone for battery fault simulation. So here with this platform, we are able to provide a synthetic data set with 5 to 6 different battery faults, for example, like different short circuits, a normal internal resistance, or even other lithium plating faults, and to randomly happen at different application scenarios, real-time data from the electric vehicles will be input to the simulation to generate the synthetic data for the further development of machine learning models for fault detection. Because we know the challenge in fault detection or safety monitoring is that, especially in Europe, we do not have a lot of available open access data sets where we can see safety issues, right? So we do have access to this kind of data, but everything is quite confidential, which is just between us and our industry partners. So with this platform, we would like to provide more information to all the researchers around the world to enable more synergy in developing machine learning models for fault detection. Yeah, and the last slide I would like to highlight is some very interesting simulation results that we are also looking at together with the different partners. How can we build up, this platform further for the future? For example, the ongoing work is we are also working on, as I said before, the physics-based model, right, for pack simulation, right, for large-scale multiple packs by integrating different faults that this model is not able to do, because this model is based on equivalent circuit models, which is quite easily to simulate battery short circuit, but maybe, for example, in lithium plating will be hard to handle. Yeah, to summarize, so the key message I would like to give you with my talk today are 3 points. The first point, right, for battery testing, characterization, aging test, we need to go further in automation. So especially when we would like to accelerate the development of battery technology here in Europe, and we need to automate the characterization and test, especially together with the industry partners with robotics, right? And then further enable this extracting process a physical parameter and more information with the AI models that we have developed and provided. And the second key message is digitalization. Right? So we need to further work on digitalization of battery testing. I think not only us, but also other partners in Europe. So our partners in different projects are working together here to further develop new software, new hardware platform, so that we can further, integrate the models, machine learning models, physics into testing, and make better decision with AI. And at the end, right, so the goal is very clear. We need to accelerate the way we do battery tests, right? The way we do battery characterization, the way we understand battery aging and build up aging models. And with more and more available digital or virtual battery models, we are able to reduce or replace some of the physical tests, which will be very beneficial for both production and OEMs in the development of battery products in the near future. And with this, I would like to thank everyone for coming today, and especially I would like to thank all the fundings, so not only in Germany, but also on the EU level from Horizon. And I would like to thank all of my group members working perfectly and hardly here, so with our partners from academia and industry on this topic. And we are on the way to use AI and digitalization to enhance battery production, characterization, and application here at Aachen University. Thank you.
Thank you very much, Professor Li. That was a fascinating talk and a great way to open this year's Advances in Battery Research online symposium. As of all the talks, we're likely going to have lots of questions come in from the audience, and I can see that we have received some already. So I will move straight on to the Q&A now. So let's start with a fundamental challenge in battery technology, which is aging. So Professor Li, how does battery aging impact performance, and why is it so difficult to predict accurately?
So battery aging is a very complex process because there will be different aging mechanisms happening, right? So as I explained before in the very beginning slides, there will be a lot of stress factors that will have influence, right? So on all of these different aging mechanisms, they are non-linearly connected, right? They are coupled together, and a lot of stress factors like time, like current rate, like temperature, right? So this is really challenging. So on one hand, to test it, right, to quickly, and on the other hand, to model it, right? So that's why it's very challenging, right, for predicting the lifetime, right, especially in the field.
That's a fantastic answer. Thank you, Professor Li. Now, given these challenges, automation seems like a promising solution, but how does integrating robotics and high throughput platforms improve the efficiency of battery testing?
So I showed several examples before. I mean, automation is something I think we can definitely achieve in the near future here in Europe, in Germany. I think our industry partners are working perfectly in this direction. We need to use more, robotics, right? So in handling battery testing, and but very importantly, so what I want to highlight is that not only robotics is necessary, but also the algorithms, the digital tools, the software side, right? So we need to have the software to be able to do the analysis, to be able to help us make decisions, to be able to help us to design the experiments, right? So this is something urgently needed in Europe. And that's why that's also the focus of our research.
Excellent. Thank you so much, Professor Li. Now, we had a question towards the end of your presentation surrounding the 2000 cell tester that was collecting data. And the question specifically was how many different sensors are in each cell of that 2000 cell tester, and how often is data actually collected?
So so the project that we are working on started last year, and the first year we focused a lot on characterization tests, the photos I showed before, right, building up the robotics and for characterization, and we just started recently the second working package, which is related to this aging test with 2,000 channels. So the sensors we are using there is the current, voltage, and temperature sensors, but we also look at other, like we will do CT measurement. We'll also do ES measurement at the beginning and the end of the aging test. And also we also several of the cells, we also look at the influence of mechanical deformation. That's why we will have the sensors to measure the deformation of the battery cells. So that will be another a signal that could be coupled quite well with the CT measurement that we do at the beginning of the and of the end of the test.
Excellent. Thank you, Professor Lee. Now that brings us to the role of machine learning, which you covered extensively throughout your presentation. How does combining physical modeling with machine learning enhance battery performance analysis?
So a very good question. That's actually the most important information I want to highlight today, and also in a lot of other talks I have given recently. Um, Machine learning model is very strong, right? When we have a very good data quality, and the physical model is very strong if we understand the physics, right? They both have limitations. Yeah, and for different cases, we just need to find the best model structure. Yeah, so I think there's one slide I showed before. So this one. So you can see on the left-hand side. Yeah, we roughly divide the current cases in battery research and development into three groups. The first group will be where we have a quite large data set, but we have some difficulty to understand all the physics. So this could be some cases like field data, right? So we have a lot of electric vehicles a long time, but the data quality is bad and it's not time series data, even some histogram data, statistical data, where it's hardly to integrate physical model there. And for that case, right, so we can use machine learning, right? Even this is a black box. Yeah, because machine learning help us to understand these hidden patterns in this large data set. And on the other direction, right? So we for example, in the laboratory, in aging test, where the data is quite clean. Yeah, the data are logged with a very good sampling rate and just several cells, charging, discharging, yeah, and several temperatures. And for that, we can use physical model very well because we have the correct input, right? So for the physical model, and several of the mechanisms we already have understood quite good, right? So what is lithium plating? What is SEI? What is cracking? We have some model which can be very useful for us to parameterize directly, which help us to do the prediction. And especially for this case, why machine learning is not very powerful is because the data limitation. We have a small data set, right? So for machine learning, if we build up a model based on this data set, the model itself doesn't see a lot of other data sets which will happen that will have very possibly overfitting, right? The generalization ability of the model could be bad. Yeah, but for some other cases, they're always in between. We have some data, we know some physics, but not everything. And for that, we need to understand, okay, both model is not perfect, but how can we combine them together? Right? There are different strategies. I showed up this on the right-hand side, right? So you can also have a detailed look in this paper. We can use the structure of the physical model and use AI to parameterize it, right? So we keep the physical constraints. Yeah, we can also enhance, right? So the structure internally, we have internal connection, right? So two examples, we can model the unknown mechanism as a neural network inside a P2D model or the agent model. And for machine learning model, we can, so I think there are also a lot of discussions in the so-called explainable AI. And we can also look at how can we do physics-informed machine learning, physics-informed neural network. Right? That's all the efforts that we are working on together to combine the physical equations that we understand and the black box models together.
Another fantastic answer. Thank you, Professor Lee. Now, I believe we have time for one final question today, which is looking ahead to the future, how do you see the future of battery testing and product development evolving with advancements in AI and digitalization?
Yeah, that's exactly the topic I'm talking about today. I also summarized the The future, as I mentioned here in last slide, I do think that we do have a lot of diagnosis models, right? So where we developed a lot for field application, for BMS, for simulation. Yeah, and now it is the time, because we need to accelerate the way we do battery testing, characterization, and aging characterization. We need to further think about, based on all of these digital models, no matter machine learning, no matter like physical models, equivalent circuit models, empirical models, why not integrate it further in our testing process, digitalize the way we do tests and accelerate it. So also with robotics, and we have a lot of facility here. That's why the goal of our research is to provide this methodology as soon as possible so that this can be transferred to all the industry partners in Europe and also in the world, right? So to help them accelerate the way they do testing, right? Because we need this large number of testing channels, not not means that okay, you also need so many channels, right? So for your testing, we need it because we would like to accelerate the way we develop it, right? So with more channels available, we can quickly try different, right, strategies, the way we do design of experiment and the way we do this high throughput testing. And we would like to provide the methodology so that you can transfer it to your company and to your research group and to your battery product. And with the AI tools, the physical models that we are currently developing in the very near future.
Thank you so much, Professor Lee. That's certainly an exciting vision for the future. But unfortunately, that is all that we have time for today. As mentioned, any questions that we didn't have time to get to will be sent to the speaker after the event. And as with all the other talks in the event, this talk will now be available to view whenever you want for the next 30 days. So that just leaves me to say thank you once again, Professor Lee. We very much appreciate you sharing your expertise with us today. And to everyone in the audience, we'll be back soon with the next talk.
Thank you. See you next time.